Section 5.1, Graphing Linear Equations. Determine the slope and y-intercept and then graph each of the following. So they want us to take 5x plus 12y minus 36 equals 0 and figure out the slope and the y-intercept. So as we saw at the end of chapter 4, if you want to do that, you need to solve for this equation for y. So if we're trying to get this y by itself, then we're going to want to move over the 15x and the negative 36. So I would subtract 15x from both sides to cancel that out. And then I would add 36 to both sides to cancel out that 36. And if I do that, I have 12y, it would be left on the left side, equals negative 15x and plus 36. And then I want the y by itself. The 12 is connected by multiplication, so I would divide by 12 to cancel that off, but I have to divide the other side by 12 as well. And when you're trying to get things in slope-intercept form, what you want to do instead of dividing the whole side by 12 is do the equivalent, which is to divide each term by 12. So then we get a y equals form, and we would just want to reduce it. So I see on these two, they're both divisible by 3, so 3 goes into here 4 times and into there 5. And here the 12 goes into the 36 3 times. So for the first term, I have left over a negative out front and the 5 over 4, and then I'll pull the x off to the side, and then plus 3. And at that point I have things in slope-intercept form, so I can read off the slope. The slope m is the coefficient of x, negative 5/4, and the y-intercept is 0, comma, whatever the constant term is, which would be 3. So I have a slope of negative 5/4 and a y-intercept of 0, 3. And now they want me to graph that. And I think these numbers are all small enough I can number in 1. So I'm going to go ahead and do that. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. I don't think I'm going to have any action over here on the left side, but I'll go ahead and provide a scale there as well. And then I'd always start off by plotting my intercept, so over 0, up 3. And then use this as rise over run. So let me do a little extra scratch work here. Change in y over change in x. Put the sign in the numerator. So over 4 and down 5. So from here I would go over 1, 2, 3, 4. Let me grab a pencil for that real quick and do that lightly. So over 1, 2, 3, 4 squares. And then down 5 because of the negative. 1, 2, 3, 4, 5. So right there. That would be my other point on the line. So I have the original point, which is the intercept, and the new point from the slope over 4, down 5. And then just grabbing a ruler, lining things up decent, and connect that with a line. So everything on that really is review. I think that's the first time we've put all of that together. So we've used slope and intercept to graph before. In the end of chapter 4 we solved for y to find slope and intercept. Now we're just putting it all together into one problem. So let me show you a couple other examples of the same thing. So on this one I want to get y on one side and everything else on the other. I'm going to go ahead and add 6y to both sides to move the y term to the left. That gives 6y equals 4x. Then I would divide both sides by 6 to cancel off that 6, and I would reduce on the other side. Those are both divisible by 2, and if you cancel the 2 we get a 2/3, and the x is still there. Now there's no constant term on this one, and that implies the constant term is a 0. And so when you go to do your slope, you can do it just like always, coefficient of x, 2/3. When you do the intercept, you know it's an ordered pair and it's going to be 0 something, and the something would be the number added here. If nothing's added, that implies that the y-coordinate is also a 0, and then we should label that. So that was our y-intercept right here, and our slope right there. Alright, so we've determined the slope and the y-intercept. Now we want to use those to graph. So start off with our intercept, over 0, up 0. Provide some scale, so 1, 2, 3, 4, 5. 1, 2, 3, 4, negative 5, and same thing on the vertical. And start off at 0, 0, and then from there, this is rise over run, or change in y over change in x. So change the x by 3 over 1, 2, 3, and then rise up to, that would put us right here. So over 3 up 2 from the origin, but really from the Y-intercept, which in this case happens to be the origin. And then get this lined up, draw in our line, and that's it. Alright, and then just one more case of this. So the thing that was somewhat interesting about this one is there's no constant term, so we need to know how to deal with that. That just means your Y-intercept is 0, 0. On this one, when we go to solve for Y, we would subtract 5 from both sides. The 5's cancel, and we just get Y equals -5. So the thing that's interesting about this one is there's no X term. But if there's no X term, what that really means is the coefficient of X must have been 0. So you don't necessarily have to write it this way, but this kind of shows you how you can view this in slope-intercept form. 0 times X is 0, which would just leave the -5. If you write it this way, what it helps you do is see the coefficient of X for the slope, m equals 0, and then you can see your constant term for the Y-intercept is -5. We always have the 0 for the X and then a -5 for the Y if we're talking about the Y-intercept. And the other way you could have known the slope is 0 is if a line only has Y in it, then it's a horizontal line, and all horizontal lines have a slope of 0. And then just finishing this off like the other ones, we want to throw some scale on. And numbering in 1 should be your standard. If that's going to fit all your numbers, go for it. If there were numbers that were too big, you might have to switch to 2s, 10s, 100s, depending on the size of the number. So over 0, down 5. Nice big dot there. Now the slope is interesting. Like, really what we want to recognize is just that this is a horizontal line and draw it in. But if you did think of it as change in Y over change in X, it still would work. Remember, our slope was 0, so that's 0 over 1. So you could say that what you need to do is go over 1 and up 0, which would just put you right here, right next door at the same height. And if the height of both of those points is the same, you just get a horizontal line. To be honest with you, I wouldn't use the slope there like that. It works, but I would just recognize that when I have a Y equals a constant line, that's always a horizontal. So I would just go down to my intercept and then draw in the horizontal line, and that would be that. Continuing on with page 2, they want us to find the X-intercept and the Y-intercept and then graph. So on the previous page we were finding the Y-intercept and the slope in graphing, which you can do, but when your equation has an X and a Y both together on one side, I think it is actually faster to find the X and Y-intercept and then graph it. So let me just show you how to do that real quick. If you were looking for the Y-intercept, we already know that the X for that is always 0. Because if you're on the Y-axis, let me go ahead and label that. If you're on the Y-axis, then you haven't moved right or left, so the X is 0. But for the X-intercept, if you're on the X-axis, then you haven't gone up or down. And if you haven't moved up or down, that means the Y value must be a 0. So when you're asked to find the X-intercept and the Y-intercept for an equation, what you would do for the Y-intercept, which we already are familiar with, is plug a 0 in for X. And now if you want the X-intercept, plug a 0 for Y. So let's just take those two steps and see what we get. So first a 0 for X, so I'm looking for the Y-intercept right now. That would be 20 equals 4 times 0 minus 5Y, so this just cancels out because of the 0. So we get 20 equals -5Y, and then we would divide both sides by -5. Here they cancel. On the other side we would simplify that, and Y would be equal to 20 over -5, which is -4. And I could fill that in, and that's fine the way it's written, but just to kind of make it look like our normal intercept, I'll add those parentheses, and there's our Y-intercept. So the X-intercept is very similar. So I'm going to do essentially the same thing, but I just want to show you a little trick that I usually use, because I don't typically write all this stuff out. If they say to find the Y-intercept, and I know I'm plugging a 0 in for X, I usually just cover the X term up. Because if you look at what happened, we plugged in the 0 and that term canceled out. So I just kind of cancel that out by covering it. And I see that 20 equals -5Y, so I think in just one step I can do that in my head. Divide both sides by -5. 20 over -5 is -4. So if I want to try that same sort of strategy here, then to plug the 0 in for y means this term will go away. 5 times 0 is 0, and that cancels out. So plugging the 0 in for y is equivalent to just covering up the y term. And if I did that, I get 20 equals 4x. So what I'd want to do then is divide both sides by 4, and 20 divided by 4 is 5. So that's kind of the quick version of finding those intercepts. So we've got the X-intercept and the Y-intercept now. I'm just going to show you the one I just did by hand as well, where I write it out. So I would plug in the 0 there, that would cancel. Then I would divide both sides by 4, and x equals 20 over 4, which is the 5. So that's kind of the math on it, but usually with the 0, because it just cancels out that term, I tend to try and do those in my head. Now as far as the graphing goes, I would look at all of my numbers over here to see if I had any big numbers that needed a scale of 2s, 5s, 10s, something like that. But the biggest number is 5, so I can just use the standard scale all through here of 1s. So I'll just label that out real quick. Pop my points, connect them with a line, and we'll be done. So over 0, down 4, over 5, up 0. Grab the ruler, line it up, draw on the line. So personally, I think that's a little faster and easier than using slope-intercept form. Instead of having to do the rise over run, just find two ordered pairs. Now sometimes finding two ordered pairs can be a little time consuming, but not when you're plugging in zeros, because it's just so fast. You're just covering up this term, divide by -5. Cover up that term, divide by 4. So zeros are a little special. I feel like you can get things filled in pretty fast with that. Alright, let me just show you a couple more examples of the same idea. Separate that one off. So moving on to part B, 2x minus 4y minus 8 equals 0. This technique of using intercepts works a little better if you have x and y on one side and the constant term on the other. So I'm going to add 8 to both sides to move that constant over. That gives 2x minus 4y equals 8. And then I'm going to want to make a table of x's and y's, but if you're asked to find intercepts, you don't just plug in whatever you want. It has to be a 0 for x, that's going to find your y-intercept. And then it has to be a 0 for y, which will find your x-intercept. And in a way, we've kind of lost some freedom here. We don't plug in whatever we want. They said x-intercept and y-intercept to graph, so I have to plug those zeros. And by the way, if you plug two different points and graph it, you'll get a line that looks right. But on my math lab and by me on test, you would get marked wrong because you didn't follow those directions. So you're losing some freedom, but the thing that they're forcing you to use, or I'm forcing you to use if you want, happens to be the easiest numbers to plug in. If you want to plug a 0 in for x, that just wipes out your x term. So you'd have negative 4y equals 8, divide both sides by negative 4, 8 divided by negative 4 is negative 2. Plug a 0 in for the y, that covers up that term or wipes that term out. You get 2x equals 8. Divide both sides by 2 and x equals 8 over 2 or 4. So intercepts are nice and quick to find, and so you shouldn't mind that they want you to use those. And now we're going to go ahead and graph them. All of these are small numbers, so standard scale will be fine. So this may, get a little irritating to have to do this every time. But scales are not always numbered in 1. Sometimes it is 10s, 20s, 30s, stuff like that. And if you have labeled nothing, people are left guessing what your scale is. So you have to number at least enough so that people can see what numbering you are using. So over 0 down 2, over 4 up 0. There's our 2 points. Go ahead and connect those with a line, and we've got our graph. And I guess it's worth mentioning at this point that you could do a third point. If you do a third point, it's just a check on your work and seeing if all three line up. But I will caution you on this, the third point will take a lot longer because you can't just cover up. So once you start plugging in another number, like maybe x equals 5 or something, you're going to have to do algebra to solve for the y, and you might get a fraction as well. So using the intercepts is a faster method, and I would typically forego the third point here, but you're welcome to do it if you want to play it safe. But that will slow you down a bit. Alright, let's look at one more. The tricky thing about this one is that it's got fractions in it. But one of the things we learned in Chapter 4 is if you have an equal sign or an equation, you don't have to deal with fractions. If you can figure out the LCD, which in this case would be 12 between the fourths and the thirds, then if you multiply every one of the terms by that LCD, that will clear your fractions out. So I'm going to do just that. Multiply every term by 12, and that includes terms like constant terms of 1 that don't even have fractions. To keep the equation balanced, every term has to get multiplied by that 12. And then what's important about that is if that's the LCD, all these denominators will go in or therefore cancel out. So I can cancel the 4 and the 3 into the 12, and then look at the leftovers, 3x minus 4y, and equals 12. And this is the kind of format I want for doing intercepts. So I set up my x and y. 0 for x will find the y-intercept. 0 for y will find the x-intercept. And then let's see what they are. 0 for x, so the x term goes away. Negative 4y equals 12. Divide both sides by negative 4. 12 over negative 4 is negative 3. Plug in a 0 for the y, this term goes away, 3x equals 12, divide both sides by 3, 12 over 3 is 4, and there's my intercepts. And one of the things that I think they want you to notice on this is that when you have a 1 on this side, then whatever number is underneath these turns out to be the intercept number. So underneath the x we had the 4, and underneath the y we had the 3, and the negative out front would make it a negative 3. So theoretically you could memorize that if you had a 1 here, this would be the x coordinate of the x-intercept, and that this, including the sign, would be y coordinate of y-intercept. Personally, I miss that most of the time. I don't notice it's that form. I would just do this work and plug in the zeros and see what I get. Alright, so let's go ahead and finish this off with a graph. We'll throw the scale on there. And again, all of our numbers are nice and small, so we get to use those ones again. And over 0 down 3, and over 4 up 0. I think that's almost the same line we had up on the previous one, I guess not quite. Line it up, and draw on the line. So this is one of my favorite ways to draw the graph of a linear equation, is to use intercepts. I really like plugging in those zeros for a couple reasons. They're easy to plug in and see what the other number is, and it's also, I think, a little easier to graph when you're on an axis than when you're off into one of the quadrants. So for a few reasons I like it. If I'm already in slope-intercept form, y equals mx plus b, I probably won't find the x-intercept because that can be a little messy. I'll just plug in other points. But when you have this, what we call standard form, x and y on one side and the constant on the other, intercepts is a great way to get the graphing job done. So moving to page 3, we just have a summary of what we were looking at on the previous page. The intercepts of the graph of an equation. For an equation that contains the variables x and y, if you're trying to find the x-coordinate of the x-intercept, substitute in a 0 for y and solve for the x. If you're trying to find the y-coordinate for the y-intercept, substitute a 0 for x and solve for the y. And that's what you saw us doing on all those tables on the previous page. So this is just a summary of that. And then one last example that's a messier one where we would use the calculator to help us through it. So let's approximate the x-intercept and the y-intercept and then graph. And because it's messy, we'll round the intercepts to 2 decimal places. So I'm just going to make my standard table, maybe a little wider because I'm going to get some messier numbers in there. And if I plug a 0 in for x, what do I get for y? Well, this is a little messier, but this term still goes away. And to solve for y, I would want to divide both sides by 4.72. So I think I'll write it out here. I'd get 4.72 times y equals 26.36. And that would be the x term gone because I plugged in the 0. And then I would divide both sides by 4.72, and whatever I get for that would be the y-coordinate of the y-intercept right here, which I'll round to 2 decimal places as they requested. And I'll hold off and set up the other one, then do both on the calculator. If I plug the 0 in for y, that's going to find the x-intercept. That's also going to make that term right there with the y drop out. And so I'd be left with negative 7.29x equals 26.36. Again, if I plug that 0 in for y, the y term would go away. I want x by itself, so I would divide both sides by negative 7.29 to cancel here on the other side for balance. And then I'll go to the calculator and see what I get for those two. Alright, so let's have a look at those. If I do the first one, it's 26.36 divided by 4.72. So that would be 5.58 if I just round that to 2 decimal places as they requested. And then on this one, 26.36 divided by negative 7.29, and to 2 decimals would be negative 3.62. And this one would be the Y-intercept, and this one would be the X-intercept. And once I have those, I can go ahead and graph them. So just do my standard move of throwing the scale on there. Even with these messy decimals, we still don't have big numbers. So the standard 1, 2, 3, 4, 5 is going to get the job done. And then plotting these as best I can, over 0, up 5.58. 5.5 would be 5.5, so it's basically halfway between the 5 and 6, erring on the side of going a little closer to the 6 because of the 5.8, but basically in the middle. And the same thing here, negative 3.62 is left 1, 2, 3, and then a little more than halfway to the 4, so trying to go basically between negative 3 and 4 with just being a little bit closer to the 4 than the 3. Because negative 3.62 is closer to the negative 4 than the negative 3. And then at that point I've got my 2 points. I'm going to draw in a line, connect with the line, and we're done. And that finishes off section 5.1.